All right, so we're in the throes of acceleration, and we understand the definition of average acceleration. Average acceleration is, the change in that velocity over a change in time. But in this class, like I said before, the majority of our average accelerations are going to be constant accelerations. So during that motion, that acceleration will remain consistent. The amount of speed changing per second will remain consistent. And that lets us be a little more concrete with our analysis of the motions of problems. And what we can do is kind of write our equation, our average acceleration equation, more of a shorthand, because if we understand the average acceleration is now constant, well, then that acceleration is always going to be the same value. So I'm just going to call it A, acceleration. And of course, change in velocity is final minus initial. And since our change in time is, we always start at time 0, we're just going to call our time t, because t2 minus 0, well, if I always that minus 0, because we always start with the initial time of 0, it doesn't make any sense. So I'm just going to call the amount of time traveled t. And this is going to create a bit of a shortened version of the average acceleration formula. And then, of course, I can algebraically rearrange this, and if you scoot a couple things around, you get v2 equals v1 plus a times t. This is one of the common formulas that we will be using over the year. And like I said, over the year, this is going to come around again and again and again. So it's not just for this particular unit. We will need this motion formula. Who knows when it's going to pop up again over the year, but it does constantly. We're gonna put this formula off to the side. So I want to take and show you another formula. Velocity average. Now velocity average is delta x over t. But what's wild is the following. When we have an average velocity, when acceleration is constant, I have a little graph kind of showing us this. Well, if I take the average of a velocity of 2 and a velocity of 6, and I were to add those together and divide by 2, I will get a velocity of 4. It's just a mathematical average, but the mathematical average is going to fall on that graph, on that same motion, because of the constant acceleration. And I should have been clearer if this were happening at 1 second and this were happening at 3 seconds. Let me clear that up a little bit. So we have a velocity of 2 meters a second at 1 second, a velocity of 6 meters per second at 3 seconds. Well, if I take that average velocity, I end up with 4 meters per second in the average of that time, 2 seconds. It will match. And this will work for any situation so long as the acceleration is constant. So what we can do here, unlike what I warned about earlier in the course, is I can actually say, well, average velocity is literally the mathematical average. But again, this only works if acceleration is constant. And that creates this formula. If I do some rearranging, it takes on the form little algebra there to rearrange the letters. But this is a second version of acceleration formulas that we'll be using. No, there is not an acceleration variable in here. There's no a. But this works for acceleration. And it also works for acceleration because if velocity were constant, if this velocity was the same as this velocity, well, you'd just be adding the two of the same velocities, but then dividing them by 2, so you'd be getting that same constant velocity, right? If our constant velocity was 10 meters a second, well, if I take 10 plus 10, but then divide it by 2, I end up with 10. And that would make sense because a change in distance would be equal to the velocity times the time, which would be this original formula. So it works, but it even works, again, with an acceleration situation. So it's really, this formula is not really the right formula to use when it's just a constant velocity. It doesn't really make any sense to use it during a constant velocity, but it does make sense to use it during an acceleration, a constant acceleration. So we'll put this over here. All right. Now, let's take this formula and we're going to go a little nuts here and we're going to substitute in for V2 with our previous formula. Why would we do that? Well, sometimes given certain problems, we're only given certain variables of motion, but yet we do, with those variables, we will have enough information to solve for other things. So if I take this formula and I put it in here, so I'm going to expand this out. Delta x equals 1/2 v1 plus v1 plus at. Oopsie. Yeah, that's right. Times t. And if I go and combine things, 1/2 2v1 plus at t. And I distribute the half and I clean things up. And I distribute the t also. I end up with this formula. Change in distance in a constant accelerating system is equal to, well, that initial velocity times the time that it's traveling, plus any gaining distance from the acceleration. 1/2 at squared. So this term would be as if the distance, if it were at a constant velocity. Obviously, if I'm at a constant velocity times time, I gain some distance. But we're not at a constant velocity. We have an acceleration, so that's going to either add or subtract to that distance that would have been possibly traveled at the constant speed. So I'm going to put this formula over here, and I have this. So that's pretty good. Okay. For this last one, it gets a little obnoxious, but let's go through it. We have our definition of average velocity when it works in a constant acceleration situation. I'm going to go back to the constant acceleration formula. And what I'm going to do is kind of merge them together. I'm going to take this formula here and I'm going to rearrange it to say t equals v2 minus v1 over acceleration. And then I'm going to plug that into this formula. Actually, what I'll do, it's a little easier. I'm going to rearrange this for t. So it's getting a little messy, so I'm going to put t equals v2 minus v1 over a over here. So that's fine. Get rid of this and let's rearrange this for t. So t equals 2 delta x over, and I'm going to, instead of v1 plus v2, I'm going to make it v2 plus v1. It doesn't matter, it's staying the same thing. And so now I'm going to put that over here. So So I have those two forms. Time equations coming from two different definitions. And now, since I have time equal this and time equal this, that means I can set these two things equal to each other. So I'm going to say V2 minus V1 over A equals 2 delta X V2 plus V1. So you can see, depending on the problem, you can solve for really any variable that you want, but in this particular case, we're going to solve it for the form of, for the V2, final velocity. We want to find final velocity. So if I start to rearrange this formula, I'm going to do a little cross multiplying here. Here, you can see I have like kind of a perfect square situation going on here. If I do the foiling, I will end up with the following. The two middle terms, if I FOIL, they drop out. One's a plus, one's a minus. I'm left with this. And then if I do some rearranging, that's the final form. This is the one formula of the 4 acceleration formulas that is called the time-independent formula. Note, there is not a time, there's not a t in the formula. We have velocities, acceleration, and displacement. And so to complete my little table, there you go. So these are the 4 formulas, and you need to know them. The AP people on the formula sheet do give you all these formulas on a formula sheet, except for this one, because this is what they consider conceptual, where that average velocity is equal to the literal mathematical average, the two velocities divided by 2, when acceleration is constant. So, next, we're going to put these to use in all kinds of wonderful situations. I'm going to go through a couple examples just to get you started.